Greetings, everybody. Let's take a look at our kind of final ending up discussion of Green's theorem. So once more, we'll start off with a statement of Green's theorem. So now we've got a region D in the plane, and the boundary of that region is our curve C that we can give a positive orientation, and we can parameterize that thing with smooth functions, with a finite number of smooth functions. And if we have this vector field with component functions P and Q that have continuous partial derivatives on an open region that contains D, then the curl of that vector field, the double integral of the curl over that region, is going to be equal to, or pulls back to, the integral of that vector field, the line integral over the boundary of that for our vector field. And so we characterized D as being the set xy, where x was going to be between a and b, and y was going to be in between two separate functions, g2 and g1, g2 on the bottom, g1 on the top. So our boundary could be laid out in this way, so that we had our boundary of D just looking like curve C1 plus C2 plus C3 plus C4. And so again, kind of getting reviewing just a little bit, we had our double integral of the partial of P with respect to Y of dA, so that kind of second component of the curl, we integrated that and said, oh, that was going to be the integral over the boundary of just our P dx. So now, what about partial Q partial X? What do we do with that? Well, the idea is that if we can break up the region into pieces bounded by functions of y. So the thing that made that first one so nice and easy was that we could parameterize it pretty easily as functions of x, either where x was going to be constant on the left side and the right side, and then we had just this nice y as a function of x for the top and the bottom. And so kind of the thing that makes the proof especially difficult or maybe hard to visualize is this part. So can you take this region and kind of break it up into those pieces so that we can get these nice parameterizations out of it? And so what we can basically do is to say, all right, you know what, whatever this shape is, so we just kind of got a random shape here, whatever this shape is, let's see if we can find points where we can break this thing up and make our x values functions of y, so that our region D's just look like the difference between two functions bounded top and bottom by x as a function of y. And so if we kind of look at this first point, we take that topmost point, and if we kind of go through these, we can divide this up into regions D1, D2, D3, D4, and D5. And so that for D1, we've got curves C1 over here on the bottom that we can make this one as a function y, or make x as a function of y for this one. For C2, we can make x a function of y for this one for the top, and so we can get that part of the curve here for C1 and C2. We do the same thing between these points for D2. We do the same thing for the region D3, so we've got just our vertical line segment, and then we've got kind of looking at these things for this, we can kind of break this up into two separate parts. We've got this region D4, we've got this region D5, and really we've kind of got this region D6 up here, but it's a little too small to write anything in. And so we've really got 6 regions that we can parameterize these curves for. And so that's kind of the idea of what we're doing when we say that. So if we have our curve CI, just being either the top curve or the bottom curve, as we kind of had those things laid out. Then if we look at the double integral over these regions d sub I of partial q partial x dA, same thing kind of applies. We just integrate with respect to x first. And when we do that with these nice parameterizations, what we get is something similar to what happened with our first integral, that we get something that kind of looks like, oh, this is the function evaluated at, so this looks like the evaluation along a curve. This looks like the evaluation along a curve. And sure enough, the top one and the bottom, getting our orientations precise, that these things just look like the sum of the line integrals of c of I plus 1 q dy plus c sub I of q of dy for the regions that we had in each one of these segments. And so kind of a little bit hand wavy, but it's giving you the idea that if we can find a way to divide up our region in this way so that we can do this, it's exactly what we need in order to complete this proof. And so if we put all of these regions together, so we take our region D, we divide those up into the sum over all of these regions that we partitioned it for, we evaluate those, and so we get line integrals there, we're still summing over all of those, we're putting all of those line integrals together, and so we end up again getting our boundary of D as we're kind of putting those together. So that one's maybe not quite as general as what we could do, but again, it would take a lot more machinery to kind of get through and to give a complete and total description of all of those. But this kind of gives us a hand wavy way of looking at it, to see that, oh, okay, this makes sense as to why this is going to work. As long as I can partition my region in just the right way, get my parameterizations the way that I want, yep, this is going to work, and that makes total sense. And so if we kind of put our two results together, what happens is our double integral over partial q partial x dA, that was the line integral of q dy. And negative of the double integral partial p partial y dA, that gives us our line integral over the boundary of p dx. So putting those, just adding those together, and we get the ultimate result for Green's theorem. Now, kind of recapping a little bit, what this really kind of hinged on was us being able to break up our region into these regions, into these subregions, that gave us the parameterizations that we really needed. And kind of to delve a little bit more deeply into that, or to look at that, to point you into the direction where you can get more information from that if you wanted to, then we could do maybe a possible video on this later on as well. But we're looking at kind of a starting point is starting to look at the implicit function theorem and what happens when our Jacobian is one-to-one and kind of implications of that. And so this is probably a pretty good place. We've got an idea of how Green's theorem works, hand-wavy argument as to a proof for why this might work, and hopefully I will see you guys next time.